I'm going to talk about using entanglement to understand the ground states of quantum materials, where like if I have like a conductor, there's a lot of interaction between the atoms by exchanging the electrons, and that makes it very complicated if you wanted to solve it on a computer, for example, because there's all this entanglement. And oh, that's the title. So it says, are topological degrees of freedom hidden in the entanglement spectrum? This is representing a material with a cut in it, and that's the entanglement between the two. So if you imagine a material with a lot of atoms, and I divide it into two parts, I have a wave function, which is very complicated entangled state. Classically, you could just describe the state of the system by saying this atom is in this state, this atom's in that state, that atom's in that state, and then you would know what the state is. But quantum mechanically, you can't define the state of an atom by itself, because it might be in several different states which are entangled with states of the other atoms, and you only know the whole state if you know how everything's correlated. So to simplify that a little bit, instead of talking about how every single atom is correlated, we can just divide the system into two halves, just as a start, and say how is this half correlated to that half? And then you might expect, if you have a system with like local interactions, that you'll have local correlations. So then I'd have a wave function that is the sum of a state of this half times the state of that half, summed over many different states. And if you know this state, the state of this half, that determines the state of that half. And because you have local correlations, that knowing this half shouldn't affect the state of the atoms really far away. So it shouldn't be that complicated to describe these correlations, because you only have to say, for the state of some atoms close to this boundary, how is it correlated to the state of the atoms on the other side of the boundary? It sounds that it wouldn't be that bad. Except that how do you describe the state of the few atoms near the boundary? Because the few atoms near the boundary are correlated to the few atoms a little bit farther away, which are correlated to the atoms a little bit farther away. And you just can't describe the state, any state of the system, just by a few atoms. So that's kind of a puzzle which has been partly solved with the idea of DMRG, which is an algorithm for solving one-dimensional systems numerically. But the theoretical concept behind it is that instead of writing the state of every single atom here, you focus on some operators, some properties of a few atoms near the boundary, and just give the eigenvalues of those operators. So those operators, the trick is that those operators won't be the full operators describing these three atoms, for example. Because if you describe all of those operators, some of those are going to be correlated to the next layer over, and we're going to get back to the same problem. The trick is you take some sort of subset of the operators that sort of gives half the information about these three atoms, and only gives the half of the information that you need to know what the atoms are on the other side. So I'll give an example of that later on. So I'm going to talk about this idea in the context of topological phases, because this is one place where there's some really interesting consequences of this idea, and it also makes it more concrete just to think of a specific example. So we'll come back to entanglement in a little bit. But there's the effect, the fractional quantum Hall effect, where entanglement turns out to be really important. And the experimental property, one of the basic experimental properties of it, is that, so what you have is you have a two-dimensional electron gas in a magnetic field. And you see various things. one of the things you can see is that if you try to drive a current from one side of the sample to the other side of the sample through a spot where the sample gets very narrow, this just represents like the boundaries of the sample, and there's a constriction there. You can measure the charge of the carriers by looking at the fluctuations of the current. You have, since the current comes in quantized pieces, you don't have a constant continuous flow of current. You have shot noise of particles coming. And by measuring the you can't see the individual charges, but by measuring the fluctuations, you can see what their magnitude is. And it turns out that the magnitude is a fraction of an electron, for example, like 1/3 of an electron or 1/5 of an electron. It's always, usually, except in some strange phases, it's always an odd fraction of an electron. So that's strange, because there's not quarks in these materials. So how do you get fractions of electrons? And an experimental property of this phase is that theoretically predicted, but it hasn't been like completely proven experimentally, I think, is that if you take two of these excitations and exchange them, they're not fermions or bosons. They're anyons, which means when you exchange them, the wave function picks up a phase of like pi/3. So that's something you can, from the theory that describes the wave function, you can calculate that phase, but it hasn't actually been measured. So these are some properties of the excitations. And if you think about this as like a phase of electrons, similar to like a solid is a phase of like solid, like solid diamond is a phase of carbon. These are properties of the excitations of the phase, the same way elasticity is a property of a solid diamond. And you might ask, is this really a phase? Like, is there some underlying property of this material that explains all these properties of the excitations? Is there a property of the ground state that explains that properties of the excitation? The same way as a solid has a repeated crystal order. Is there something in this phase that explains all these other properties? Because these are all properties of the excitations, they're not properties of the ground state. So I'm going to give an example of a property based on the entanglement. So here's an example of an entangled state. If I just have two electrons, which can be either spin up or spin down, I can make a singlet state out of them. And that's a definite state. But if I just measure the spin of the first electron, whatever component of the spin I measure, I get 50-50 chance to be either up or down, left or right, or everything. So that means that if you ignore the second atom, the second electron, the first electron is in a completely mixed state. Its reduced density matrix is just diagonal and incoherent. So it looks like an electron just at an infinite temperature would look. It's just completely random. So in general, we can sort of make an analogy between entanglement and thermal energy by taking our reduced density matrix and taking minus the log of that. And we just call that the entanglement Hamiltonian. And we call it a Hamiltonian because if we invert this equation, we get the reduced density matrix as e to the minus the Hamiltonian, this entanglement Hamiltonian, which is just like the Boltzmann relationship. So for example, if I have a little bit more of an interesting state than this, the eigenvalues of this entanglement Hamiltonian will correspond to these two terms, and you have like one would be log 3 halves and one would be log 3. So the bigger the entanglement energy, the less important it is in this superposition. So I'm just making an analogy between entanglement and thermal fluctuations. But the reason to do that is because, let's see if I can, is that entanglement is basically, it's fluctuations in the ground state. So we're trying to introduce sort of a dynamics for those fluctuations, so that this entanglement Hamiltonian sort of represents the dynamics of that 0-point motion that's in the ground state. Although it's sort of forced, so you might wonder if it really acts like a regular Hamiltonian. So this idea was first applied by Haldane and Lee to understand the ground state of the fractional Hall state. Because there was lots of numerics on the fractional Hall state, but they couldn't always recognize what type of state it was. And they would want to, just looking at an infinite state without complicated boundaries or anything, they'd want to be able to look at that ground state and not make excitations, just the perfect ground state, and try to figure out what the properties of the excitations would be if you excited them. So their idea was that if I look at the ground state and divide it in half, there's fluctuations in the ground state where a sort of virtual excitation fluctuates back and forth between the two sides of this cut, which means you have entanglement. So if I would just look at half the system, I would sort of make a sort of collapse of the wave function and have a fractional excitation on one side or the other. So if I look at the entanglement spectrum, I should see excitations basically along the edge. And what they saw is if you look at the spectrum of that entanglement Hamiltonian, it has a certain, the energy as a function of the momentum has a certain pattern of multiplicities that exactly matches the physical energy spectrum. How much time do I have? I just want to. Okay. Oh, good. It's better than I thought. So you can understand. You can understand this in a sort of what's going on in a sort of. So you can understand why in the ground state we can see all these fractional excitations in the following way. So like in an ordinary phases, you might not see anything special in entanglement, but a phase with fractional excitations, you have to, so what I mean is, like, what I'm trying to understand here is the excitations by looking at the ground state. Like if I have a material that maybe it has some interesting plasma waves or some other interesting excitation, I'm not going to be able to discover that by just looking at the ground state. But if you have a phase that has fractional excitations, you should be able to see it by looking at the ground state because of the following thing. If I have this phase, I can make a fractional excitation here, like pull out a 1/3 electron and move it over here. But if I do that, there has to be some kind of something connecting them. So if I would divide the system in half like this, if I look at the entanglement between the two halves, if there was nothing really special that happened along the edge, if there was nothing that connected them, then I could sort of mix and match. I could take a state with a 1/3 missing electron here, and a state with no missing electron and no additional electron over here. And if I put that together, I'd get something with a fractional charge. And this is made out of whole electrons, so that's not possible. So the only way to imagine something like this could happen is if there's always a perfect correlation. Anytime you're missing minus a 1/3 electron here, you have to have a 1/3 of electron here. And then there has to be something that connects them. You can imagine it's sort of like if you have a jigsaw puzzle, there has to be a piece sticking out that fits into a piece, like into a hole on this side. And that sort of comes out of this hole. So if that's true, though, then that would mean that there's an energy. You'd think at first that there'd be an energy associated to that line, and then you wouldn't really be able to have those particles move around independently of each other. And the only way that that's avoided is because in the ground state, there's these loops without any electrons attached to them, that they're all fluctuating around. So then if I look at the entanglement spectrum, I see these little puzzle pieces sticking off even without excitations. So that's why in the ground state you could see excitations. So I'm going to now just like look at an example in one dimension where you can make this more precise and use it to understand. Turns out you can actually understand all the possible phases in one dimension as a function of symmetry. So usually people talk about if I have a symmetry, what are the phases you can have? The symmetry can be broken in different ways. It could be completely broken spontaneously, or it could be partially broken. Like if I have a set of spins, they could order in a certain direction and make a magnet, or they might not order, so that would be like two different phases. But in this case, we're looking at phases where there's no spontaneous symmetry breaking. So you may at first think there's no phases, but there actually are phases that have some kind of special entanglement. The only way to recognize them is with entanglement. So as an example, you can imagine I have a chain of atoms with the spin 1, and I have just an antiferromagnetic between the adjacent atoms, antiferromagnetic interaction. And then each atom, to make a phase diagram, I'll add another term that forces the atom to have, if U is very large, it forces the atom to have a spin of 0. And then I have another term just so I can draw a nice, another parameter just so I can draw a nice two-dimensional phase diagram. But I don't really need that axis for what I'm talking about. So this, if you set U and Bx equal to 0, this is a really interesting Hamiltonian, because in the ground state, there's so much quantum fluctuations that there's 0 spin expectation value in the bulk of the phase. Basically, if all the atoms form singlets with each other and you end up with no spin in the bulk. But at the edge, even though there's spin 1 atoms, at the edge you have half-integer spins. So it's sort of similar to what I said in the fractional quantum Hall effect, except that they can't move away from the boundary. They're just pinned at the boundary. So how can you recognize this phase if you don't see the edges of the system? So so I'll imagine adding this other parameter U. If U is small, we're in this phase which is a special phase with the half-integer spins at the boundary. And when you increase U, there's a phase transition at this point. But nothing changes in terms of the order. The expectation value is still 0 of all the spin. But if you look at so what's going on? How can you recognize that? How can you understand why there's a singularity in the properties of in the magnetic response at that point? If you look at the entanglement spectrum, there's a big change. In this phase, every level of the entanglement spectrum is doubly degenerate. And in this phase, some are doubly degenerate and some are singly degenerate. And the way you can understand that is because if I look at a segment of this chain, and I look at the entanglement Hamiltonian of that segment, I can do the thing I talked about at the very beginning. I can introduce some effective operators that describe just the part of the system that's entangled with this part of the system. So I can have a spin operator that describes the spin of the edge, and a spin operator that describes the spin of the edge there. And then the total spin of the physical spin of all these atoms summed together should be the sum of this effective operator plus the sum of this effective operator, because in the bulk, the expected value of the spin is 0, so you don't have to include the bulk. And now, what happens in this phase is that the spin of an end is a half-integer. But since the physical spins are integers, that means the other end would also have to be a half-integer. And that means that this isn't true for just one state. It's true for the whole spectrum, because otherwise you could, since they're independent of each other because they're so far away, you could mix and match. You could make this end be an integer spin state and this end be a half-integer spin state, but then you'd have a total half-integer spin, which isn't possible because it's made out of integer spin atoms. So it means every state is either a half-integer spin or every state is an integer spin, and that's what gives the difference between those. So I'm just going to say quickly, I don't think I'll just quickly say what I'm working on, right now related to this, which is an interesting idea discovered by Zhangwan Ha. It's a phase, a three-dimensional system where you have nearest neighbor, you have local interactions between spins. So basically, it's just, if you look at the Hamiltonian, it looks really complicated, but there's nothing weird about it. There's nothing non-local or anything. It's just on each site you have two spins, And there's a complicated interaction involving like 6 spins interacting on each cube in the z components and the x components. And the thing that's interesting about this state is that if I look at it on a finite system, there's a degeneracy of the ground state, which the idea is that you might be able to use that degeneracy to store qubits, and that they wouldn't be messed up by thermal energy making particles move around and change the value of the qubits. And the reason why they wouldn't be messed up is because in this system, any excitations that could move around and could change the state are somehow locked into place. And I'm not going to explain why. I just say it has to do with some kind of a Gauss's law that if I have a surface surrounding a region, it doesn't just tell me how many excitations are inside the region, but it tells you the position of those excitations. And you can see that from the entanglement spectrum. So that's enough.